Hi. In this lecture, we're talking about problem solving, and we're talking about the role that diverse perspectives play in finding solutions to problems. So when you think about a problem, perspective is how you represent it. So remember from the previous lecture, we talked about landscapes. We talked about a landscape being a way to represent the solutions along this axis and the value of the solutions as the height. And so this is metaphorically a way to represent how someone might think about solving a problem, finding high points on their landscape. What we want to do is we want to take this metaphor and formalize it. Remember, part of the reason for this course is to get better logic, right, to be able to think through things in a clear way. So we want to take this landscape metaphor and turn it into a formal model. So how do we do it? The first thing we do is we formally define what a perspective is. So we speak math to metaphor. So what a perspective is going to be is it's going to be a representation of all possible solutions. So it's some encoding of the set of possible solutions to the problem. Once we have that encoding of the set of possible solutions, then we can create our landscape by just assigning a value to each one of those solutions. And that will give us that landscape picture like we saw before. Now, most of us are familiar with perspectives, even though we don't know it. Let me give some examples. Remember when we took 7th grade math, we learned about how to represent a point, how to plot points. And we typically learned two ways to do it. The first way was Cartesian coordinates. So given a point, we would represent it by an x and a y value in space. So it might be 5 units. This would be the point, let's say 5, 2, right? It's 5 units over in the x direction, 2 units in the y direction. But we also learned another way to represent points, and that was Cartesian coordinates. We could take the same point and say, well, there's a radius, which is its distance from the origin, and then there's some angle theta, which says how far we have to sweep out in order, sweep that radius out in order to get to the point. So two totally reasonable ways to represent a point: x and y, r and theta. Cartesian, polar. Which is better? Well, the answer is it depends. Let me show you why. Suppose I want to describe this line. If I want to describe this line, I should use Cartesian coordinates, because I can just say y equals 3 and x moves from 2 to 5. It's really easy. But suppose I want to describe this arc. If I want to describe this arc, now Cartesian coordinates are going to be fairly complicated, and I'd be better off using polar coordinates because the radius is fixed, and I can just talk about how the radius is, there's this distance r, and theta just moves from, a to b, let's say. So depending on what I want to do, if I want to look at straight lines, I should use Cartesian. And if I want to look at arcs, I should probably use polar. So perspectives depend on the problem. Now let's think about where we want to go. We want to talk about how perspectives help us find solutions to problems and how perspectives help us be innovative. Well, if you look at the history of science, a lot of great breakthroughs, when you think about Newton, and his theory of gravity, you can think about people actually having new perspectives on old problems. Let's take an example. So Mendeleev came up with the periodic table, and in the periodic table he represents the elements by atomic weight, right? He's got them in these different columns. In doing so, by organizing the elements by atomic weight, he found all sorts of structure, right? So all the metals lie in one column, stuff like that, right? Remember from high school chemistry class. That's a perspective. It's a representation of the set of all possible elements. He could have organized them alphabetically, but that wouldn't have made much sense. So alphabetical representation wouldn't give us any structure. Atomic weight representation gives us a lot of structure. In fact, when Mendeleev wrote down all the elements that were around at the time according to atomic weight, there were gaps in his representation. There were holes for elements that were missing. Those elements became scandium, gallium, and germanium. And they're eventually found 10 to 15 years later. After he'd written down the periodic table, people were not able to find the missing elements. That perspective, atomic weight, ended up being a very useful way to organize our thinking about the elements. We do it all the time now. When you have any sort of task, you'll find that you're actually using some sort of perspective. Suppose that you're hiring someone, and you've got a bunch of recent college graduates who apply for a job, and you've got to think, okay, how do I organize all these applicants? If I have, let's say, 500 applicants. Well, one thing you could do is you could organize them by GPA. You could take the highest GPA down to the lowest GPA. That'd be one representation. And you might do that, right, if you valued competence or achievement. But you might also value work ethic. And if that were the case, you might instead organize those same, CVs or application files by how thick they are, figuring the people who have really thick ones are people who work really, really hard. They've accomplished a lot. Well, the third thing you might do is you might value creativity. And you might say, well, let's put the ones that are sort of most colorful, most interesting over here, and the ones that are least colorful and least interesting over here. That's a third way to do it. Now, depending on what you're hiring for, depending who the applicants are, any one of these might be fine. The only point I'm trying to make here is that there's different ways to organize these applicants. And each one of those ways you organize them, whether it's in your head or whether it's formally laying them out in some way, is a perspective. And those perspectives will determine how hard the problem will be for you. Let me explain why. I want to go back to the landscape metaphor. And I want to think of that landscape as being rugged. And by rugged, I mean that it doesn't look like a single peak, that there's lots of peaks on it. And I want to formalize this notion of peaks. I'm going to do so as following. I'm going to define what I call a local optima. A local optima is a point such that if you look at the points on either side of it, they're lower in value. So it's sort of a point that locally is the highest possible value. So if I look at this particular rugged landscape, again, there's 3 local optima. 1, 2, 3. If I were at any one of these 3 points, I'd be stuck. I couldn't, if I looked to the left or to the right, I wouldn't find a solution that's better. So when we think about what makes a good perspective, a good perspective is going to be a perspective that doesn't have many local optima. A bad perspective is going to be one that has a lot of local optima. Let me give an example, okay? So suppose I'm coming up with a candy bar. Suppose I'm tasked with coming up with a new candy bar. So I have my team of chefs make a whole bunch of different, confections for me to try, and I want to find the very best one. But there's so many of them. There's so many possibilities. Not even sure how to think about it. Well, one way to represent those candy bars might be by the number of calories that they had. So I could organize all the different things they make by number of calories, and if I did that, maybe I'd have 3 local optima. So that's a reasonable way to represent these possible candy bars. Alternatively, I might represent those candy bars by masticity, which is chew time, how long it takes to chew them. So these would be the ones that maybe only take 2 minutes to chew, and these may take 20 minutes to chew. Well, chew time is probably not the best way to look at a candy bar, and so as a result, I'm going to have a landscape with many, many more peaks. And so because it's got many more peaks, that's more places I can get stuck. So it's not as good of a way to represent the possible solutions. It's not as good a perspective. The best perspective would be what we call a Mount Fuji landscape. That would be a landscape that just has 1 peak. And these are called Mount Fuji landscapes because if you've ever been to Japan and you look at Mount Fuji, it looks pretty much like this. Actually, not quite like this. There's like snow on the top. But for the most part, it looks just like one giant cone. If you're on a Mount Fuji landscape, if you're sitting at some point, you can always just climb your way right up to the top. So these single peak landscapes are really good because you've basically taken a problem and made it very, very simple. What would be an example of a Mount Fuji landscape? I'm going to take a famous example. So a famous example comes from Scientific Management and due to Frederick Taylor. Taylor famously solved for the optimal size of a shovel. So let's think about the shovel size landscape. So on this axis, I've got the size of the shovel. And on this axis, I've got the value. Now, what do I mean by the value? I don't mean how much I can sell the shovel for. What I mean is like how useful the shovel is at the task. So let's suppose that we're shoveling coal. And I want to think about how many pounds of coal can some shovel in a day as a function of the size. So let's start out here where the size is 0. So this is the size of the pan. Well, if I have a shovel that has a pan of size 0, that's formally known as a stick. And we can't get anything. We're not going to shovel anything with a stick. Well, as I make it bigger, as I make it the size of maybe like a little spoon or something, then we can shovel a little bit. And as I make the shovel bigger and bigger and bigger, whoever my worker is can shovel more and more coal. But at some point, the shovel's going to get a little bit too big. And it's going to be too heavy to lift, and the worker's going to get tired, and he'll shovel less and less and less and less. And then eventually get to some point where the shovel's so big that he can't even lift it, and it's as useless as the stick. So if I look at value in terms of how much coal the person can shovel in a day as a function of the size of the shovel, I'm going to get a single peaked landscape. That's going to be an easy problem to solve. And this idea that we could represent scientific problems in this way, or in particular engineering problems in this way, and then climb our way to peaks, was the basis of something called scientific management. And the idea was that you could then, by finding these high points on these landscapes, find optimal solutions. Well, you're only going to find the optimal solution, right, for sure, if you hill climb like this, if it's single peaked. If it's rugged, if it looks like this, if it looks like Mount Fuji landscape, you're fine. But if it looks like this masticity landscape, if you have a bad perspective, well, then if you climb hills, you could get stuck just about anywhere. So what you'd like is you'd like a Mount Fuji landscape, and in the case of simple things like the shovel, that's easy to get. Let me give another example. This one's a lot of fun. This is a favorite game of mine called Sum to 15, and was developed by Herb Simon, who's a Nobel Prize winner in economics. And Sum to 15 was developed to show people why diverse perspectives are so useful, why different ways of representing a problem can make them easy, can make them like Mount Fuji, or it can make them really difficult. Okay, so here's how Sum to 15 works. There's cards numbered from 1 to 9 face up on a table. Imagine 9 cards in front of you. There's 2 players. Each person takes turns taking a card until all the cards are gone, possibly, right? You could end sooner. If anybody ever holds 3 cards that sum up to exactly 15, they win. That's the game. So really simple. 9 cards, alternate taking cards. If you ever get exactly 3 that sum to 15, you win. So let me show you a game. Here's a game between 2 people. We'll call them Paul and David. Paul goes first. Now you'd think when you play this game, the thing to do would be to choose the 5. Paul chooses the 4, which is sort of an odd choice. David goes next, so he takes the 5. Paul then takes the 6. Now, the 6 is a strange choice because 4 plus 6 plus 5 equals 15, so it looks like there's no way that he can win. Well, this would be confusing to Doug, so Doug's going to take the 8. Now, notice 8 plus 5, equals 13, so that means Paul has to take the 2. So he takes the 2. Well, think about what happens next. 4 plus 2 is 6. So if Doug doesn't take the 9, he's going to lose. But 6 plus 2 is 8. So if Doug doesn't take the 7, he's going to lose. So what you've got here is that Paul has won. No matter what Doug does, Paul's going to win the game. Now this is a pretty tricky game, right? It was developed by a Nobel Prize winner. You can imagine there's lots of strategy involved. I want to show you this game in a different perspective. Remember the magic square from 7th grade math? Every row adds up to 15, 8 plus 3 plus 4, 1 plus 5 plus 9, and 6 plus 7 plus 2. So does every column. 8 plus 1 plus 6 sums up to 15, 3 plus 5 plus 7 sums up to 15. And even the diagonals. 8, 5, 2 is 15, 6, 5, 4 is 15. Every row, every column of the diagonal sum up to 15. Let me show you this game again on the magic square. This is just a different perspective on sum to 15. Paul goes first and takes the 4. Doug goes next and takes the 5. Paul takes the 6, which is an odd choice because now he can't win. Doug then takes the 8. Paul blocks him with the 2, but now it turns out either the 9 or 7 will let Paul win. What game is this? Well, you're right. It's tic-tac-toe. Sum to 15 is just tic-tac-toe, but on a different perspective, using a different perspective. So if you turn sum to 15, if you move the cards 1 to 9 and put them in the magic square, what you do is you create a Mount Fuji landscape, in a sense, right? You make the problem really simple. So a lot of great breakthroughs, like the periodic table, Newton's theory of gravity, those are perspectives on problems that turn something that was really difficult to figure out into something that suddenly makes a lot of sense. It's very easy to see the solution. That leads to something that I call in my book, one of my books, The Difference, I call this the savant existence theorem. For any problem that's out there, there exists some way to represent it so that you turn it into a Mount Fuji problem. Now, why is that? Well, it's actually fairly straightforward. All you have to do is, if you've got all the solutions here represented on this thing, put the very best one in the middle, and then put the worst ones at the end, and then just sort of line up the solutions in such a way so that you turn it into a Mount Fuji. So it's very straightforward. Now, the thing is, in order to make the Mount Fuji, you'd have to know the solution already. This isn't a good way to solve problems. But the point is, it exists. So there's always the possibility that someone could look at a particular problem and say, hey, what if we think of it this way? And in doing so, turn something that was really rugged into something that looks like Mount Fuji. Here's the flip side, though. There's a ton of bad perspectives. So just like there's these Mount Fuji perspectives, there's also lots and lots of horrible ways to look at problems. Think about it. Suppose I have just 10 alternatives, and I want to think about what are all the different ways I could just put them in a line. Well, there's 10 things I could put first, 9 things I could put second, 8 things I could put third, and so on. So there's 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1 perspectives. Most of those are going to not be very good. They're not going to organize this set of solutions in any useful way. And they're particularly not going to, only a few of them are going to create Mount Fujis. So when we think about the value of perspectives, what we get is this. There's really good ones out there that insightful, smart people can come up with really good representations of problem to make the landscapes less rugged. If we just think about things in random ways, we're likely to get a landscape that's so rugged that we're going to get stuck just about everywhere if we're not going to be able to find good solutions to the problem. And we're going to get things that look like the masticity landscape. So what have we learned? First thing we've learned is that when you go about trying to solve a problem, we encode it in some way, and that's a perspective. And a perspective creates peaks, right? It creates these local optima. So better perspectives have fewer local optima. Worse perspectives have lots of local optima. And if you think about how many perspectives are out there, we just saw there's billions of them. And because there's billions of perspectives, most of those probably aren't very useful. Some of them, though, turn problems into Mount Fujis. And sometimes it takes a genius, it takes a Newton, it takes a Mendeleev to come up with a way of representing reality so that something that was incredibly rugged becomes Mount Fuji-like. Other times, if you think about the size of a shovel, we're going to get things with lots and lots of peaks. That problem, most of us could probably figure out a way to represent that problem just by shovel size so that it becomes a Mount Fuji. But the big point is this. When we go about solving problems, the first thing we do is we encode them. We have some representation of the problem. That representation determines how hard the problem will be. If we represent it in such a way that it's a Mount Fuji, it's easy. If we represent it in such a way it looks like that masticity landscape, it's probably going to be fairly hard. Where we want to go next is we want to talk about, once we've got this representation of the possible solutions, once we have that landscape, so to speak, how do we search on that landscape? So one thing we talked about was climbing hills, but there's lots of different ways you can climb hills. So that's what we'll talk about next, the heuristics we use on a landscape. Thanks.